Going on, y'all? Welcome back. In this video, we are going to practice using left and right distributivity. Anytime we're attacked with a math problem, we're walking down the street, and all of a sudden someone jumps out of the corner and attacks us and says, "Here, solve this math problem." And the first thing we do is we take a deep breath and say, "Whoa, back up off me, fool." Then we literally read the entire statement out loud if you prefer. So let's do that together. Multiply the following and simplify. X minus 3 times x plus 5. All right, so this looks like a multiplication problem. One of the first steps I like to do in any math problem is actually write down the entire problem in my own handwriting. And mathematicians are efficient or lazy, I'm not sure which. We often suppress multiplication. So I'm going to go ahead and just add those back in, like really, literally write down the multiplication. I recognize this immediately. So one of the things that we're going to try to do is solve this in multiple ways. So the first way I'm going to do is called option 1, solve by distributivity. So let's do this in one way first, and then we'll do it in another way second. Remember from a previous video that we had these two really powerful rules. One of them was called left distributivity, and the other one was called right distributivity. I'm going to go ahead and introduce some colors. I think Gandhi once said that real mathematicians highlight using colors. Maybe that was Mandela. The point is, though, to get creative with it, that this is actually how we do our own brain justice. It's really important to really get into it. So the thing I wanted to show here was that we're kind of chunking information with distributivity. So if we have a multiplication on the right, and addition on the left, notice that we can pass that multiplication through the addition. So here, let's do this one first. So let's think about this as the chunk of information that is done with a subtraction, and we'll think about this whole thing as one piece of information. So the right-hand side there is playing the role of C, right? That right-hand side right there is playing the role of this entire thing, C. And then here, A would be X. It's not a plus, it's a minus. So A minus B, so X minus 3. And then this whole thing is C, right? So what did distributivity say, right distributivity say? It said that I could take the entire thing C and pass it to each individual chunk. So here we go. So the first chunk A times C, in this case, C is an entire chunk, right? It's that whole thing. And then I'm going to maintain the subtraction. There's B, there's the second piece of that chunk. I'm going to multiply by C. So that right there was called right distributivity. That's how we did that. What's crazy now, though, is that we have a similar problem show up again. Notice in this case, we're going to think about here's our chunk on the left-hand side. There's the A. I have a multiplication outside of A and an addition right there. So now all of a sudden, what is left distributivity tell me I can do? Well, left distributivity says that I can make it rain. I'll make it rain. Just like little Tucci, right? So here, when I take the multiplication, I can pass through the addition. I can pass one copy of that to the first part, that B part, and one copy to the second part. So here I've got X times X plus X times 5. And then the same thing here. Notice that I have a -3 outside of this, and I'm going to be a little bit cavalier. I'm going to add an addition here. So remember that -3, if subtraction is something, it's the same thing as adding that negative, right? So now all of a sudden, I can take that -3 and I can pass it to each part of the chunk on the right-hand side. So this would be -3x plus -3 times 5. And that was by left distributivity, right? Okay, Well, x times x, there are two x's. Remember that power operations count the number of x's. So x times x is x squared. 5 times x is the same thing as x times 5. In other words, we can always switch the directions of this. So this is 5x. Here I've got plus a minus 3x. So plus a minus becomes a negative. And then here I've got minus 3 times 5. So that's minus 15. Here we look at two terms that are alike, and we say that we can actually combine those. So this is called combining like terms. In other words, if I have 5 x's and I take away 3 of those, how many are left? Well, it must be positive 2x. Here I can't do anything with x squared because there's only one term that shows up like that, plus a minus 15. So my claim is this is as simple as it's going to get, right? And notice that we used 2 distributivities. We used 2 different versions, and we actually used it 3 times. We used it once here, once there, and once there. First one was right distributivity. The second 2 were left distributivity. So that's how we get down to the bottom of that one. My claim, though, one of the themes of our time together is going to be when solving math problems, try to do it in as many ways as possible. Really think about your brain as like a highway system, and the more different routes you have to an end result, the more robust, the more comfortable you'll be traveling, right? Just like in your neighborhood. If you know how to get from point A to point B in a bunch of different ways, you have a bunch of options when you're traveling. So let's do this a different way. Option 2, and this comes from my inspiration and my teacher, which is so many of my students over the years. I prefer distributivity for multiple reasons, but many students tell me that FOIL is really useful. So FOIL stands for first, outer, inner, last. So first, outer, inner, last. And what my students who use this successfully have shown me is they do this thing with kind of, so they call this first, x times x, outer, x times 5, inner, negative 3 times x, and then the last 2. And what they mean by the last 2 is this is the last one of this chunk, 5 is the last one of that chunk. So what students would do is x times x is x squared, x times 5 is positive 5x, negative 3 times x is negative 3x, negative 3 times 5 is negative 15. So now when we look at that, we can see that 5x minus 3x is what we call positive 2x. There we've got x squared. There we have minus 15. Check that out. Same result, different mechanism. I did want to call out that notice FOIL skips the inner step of distributivity. And in fact, I like to say that FOIL is the child, distributivity is the mother and father, right? Or father and father, or mother and mother, or just 2 parents, right? We get FOIL out of distributivity. That's the reason I like to do this. And generally, if I can memorize one thing and get other things for free, that's a super efficient use of my memory. And so that's why I prefer distributivity. But if this works for you, go for it. Here's a challenge for you all viewers. Can you find another way to solve this problem? Is there some other mechanism that you know in order to produce this? I've seen some people use boxes. I saw one person use an X. I've seen a bunch of different ways to do it. Have fun with it, y'all. The more ways you can travel the roads, the safer you'll be under different circumstances. Thanks so much for your attention. I'll see you in the next one.